High above the atmosphere, an artificial satellite travels through the vacuum of space at thousands of miles per hour. The Earth exerts a massive gravitational pull, drawing everything with mass toward its center. If gravity constantly pulls downward, what keeps these multi-ton machines from crashing into the ground? They are falling, but also have an immense tangential velocity, a speed perfectly parallel to the planet's surface. The satellite falls downward, but moves sideways so fast the Earth curves away beneath it at the exact same rate. An orbit is not a zone where gravity disappears. It is a state of perfectly balanced, continuous freefall. Isaac Newton recognized that the rules governing objects on Earth applied to the sky. The exact same invisible pull that drops an apple to the grass is what tethers the moon to our planet. He defined this relationship mathematically. To find the gravitational force between any two objects, you take the product of their masses and divide it by the square of the distance between them. At the same time, maintaining any circular path requires an inward force to keep an object from flying off in a straight line. Physicists call this required inward pull centripetal acceleration. Earth's gravity provides the required inward pull, so we set the equation for gravitational force exactly equal to the centripetal force equation. Look at the lowercase m, the satellite's mass. Appearing on both sides, it mathematically cancels out entirely. Because the mass drops out of the math completely, the exact required orbital speed depends solely on the satellite's altitude. A school bus and a golf ball placed at the exact same height require the exact same speed to stay in orbit. Since the weight of the machine doesn't matter, changing a satellite's altitude is the only way to alter its journey around the Earth. Decades before Newton, the astronomer Johannes Kepler mapped out exactly how distance affects orbital timing by analyzing decades of naked eye observations. He established the law of periods. It states that the square of the time it takes to complete one revolution is proportional to the cube of the semi-major axis. The semi-major axis is simply half the distance across the widest part of an elliptical orbit. As you increase the radius of an orbit, the time required to complete a revolution grows significantly. Gravity gets weaker further away. To maintain perfect freefall, satellites stationed further from Earth must travel at slower speeds. A satellite in low Earth orbit zips around the planet in roughly 90 minutes, while satellites placed higher up take hours to complete a single trip. The math dictating the speed of a communications satellite applies to every object in the solar system. This table shows the measurement of planetary motions, listing the distance and time period for the 8 planets orbiting the Sun. Check the quotient column on the far right. When you divide the square of the time period by the cube of the radius, the resulting number is nearly identical for Mercury, Earth, Neptune, and everything in between. Any object orbiting a central body, like a rocky moon making its way around Jupiter, follows these exact same constraints. Artificial satellites are simply modern, human-engineered additions to an ancient system of cosmic mechanics. All of this rigorous astrophysics started by observing the natural environment around us. The force pulling an apple to the dirt is the exact same tether holding the moon in the night sky. Every piece of satellite technology relies on treating circular motion and terrestrial gravity as two sides of the same coin. The universal law of gravitation provides a singular mathematical rule. It dictates the downward path of falling fruit, and it keeps the satellites that power our modern world perpetually falling and perfectly missing the ground.